Hello AP Physics 1, it's Mr. Ng with a lesson on dynamics. It's our introductory lesson to forces and Newton's laws. Take out some notes, let's take some notes. So what is dynamics? I think a really good way to think about it is one of our old tippers. So here, if you recall, a lot of us were goofed up by this tippers because a lot of us were trying to incorporate the mass of this rocket. So when we think about the mass of the rocket translating into this initial velocity, that's dynamics. So here, dynamics, I'm going to box them in blue. Dynamics deals with forces. For instance, this is a pretty heavy rocket. It's going, let's assume that it went from 0 to 30 meters a second. This must have had a fairly large force. Here's another fairly heavy rocket going faster. This must have had a pretty large force. But here, these guys are a little bit slower, right? And they're a little bit lighter, especially lighter than A. So maybe this will have a smaller force, right? When we talk about forces, that's dynamics. The why. Why do things move? As opposed to, say, kinematics. Kinematics is up here when we just talk about the velocity, acceleration, or displacement. Kinematics is just describing how things are moving. Right? We don't really know why. That's this chapter. Dynamics is about why things move, about forces, and about Newton's laws. So what is a force? A force is a push or a pull, and the unit for forces is a Newton. A Newton is the unit. I don't want to dig too far into Newtons just yet because we have a whole other lesson where we talk about Newtons and use Newtons when we start doing all that math. But just so you know, intuitively, forces are pushes and pulls, and here are some classic forces. One classic force is the force of gravity, which is going to be mg, right? The force of gravity is going to equal to the mass of an object times the acceleration of gravity. Acceleration of gravity. I'm gonna just say grav, right? And then we're gonna abbreviate it as just m for mass and the acceleration of gravity as g. That's the force of gravity, mg. FYI, the force of gravity is technically weight, meaning it depends on gravity, right? So if we were to go to the moon where gravity is a third of what it is here, your weight will be less, right? That's the force of gravity. The force of gravity is basically weight. On top of that, there are applied forces. Here, this person is pulling the string. That is an applied force. And FYI, I'm doing something very specific here. I'm doing these little free body diagrams. You'll figure it out in a bit. So here, an applied force is basically a force that's applied by an outside source. In this case, that freaky floaty hand. Tension is any sort of force that is pulling on it, all right? A pulling force from a string typically is tension, right? So here, tension is typically abbreviated as big T, or sometimes I try to get fancy and I do F of T, the force of tension. And then finally, as tension pulls it one way, the desk is going to oppose that motion. And it's going to oppose that motion in another force called friction. Oftentimes, it's going to be F of F, as in the force of friction. And we'll dig all into the math of those in later lessons. But just so you know, these are our classic forces. The force of gravity, mg, mass times gravity. Applied force are the forces that are added in. Tension is any sort of pulling force on a string. And friction, well, friction is going to be pretty important. Friction is any force that opposes movement. It's always on the opposite direction of movement. Again, friction opposes movement, and it goes in the direction of any movement. So if you're sliding to the right, friction is slowing you down to the left, okay? And it's based off the intramolecular forces between surfaces. That's called a contact force. Here, let's clarify that a little bit. So here, imagine as these things are being moved or rubbed, there are contact forces where the molecules, imagine they're not perfect, right? Little bumps, more than just little bumps, little intermolecular forces are occurring between these two surfaces, all right? I'm gonna make the box, I don't know, brown, right? Here's the box, and then here's the table, right? Oh, that needs to be blue. Yeah. Here's the table. There are little intermolecular forces holding the box of the table just slightly. That causes friction. Let's take a moment to practice a little. I just listed quite a few forces in the prior slide. And here is a scenario that John Colley gives us. Take a moment and doodle this down into your notebook and list at least 3 forces that are available here. Okay, you could pause the video. And as you pause the video, you might wonder, like, who is this woman? And why did she buy so many watermelon? And then you'd have to think, like, I don't think she bought those watermelon. Like, why would you be in the middle of nowhere with so many watermelon? Like, is this just one of those math things where, like, people have, like, you know, like Bob went to the market and bought 85 whatever? Like, is that what happened in real life? And then when they wrote this book, did they hire someone and was like, hey, weird, but we're gonna pose you? Like, why did they come up with this pose? Like, someone had to go to the store and buy a bunch of watermelons for this picture to exist. It just doesn't, I mean, maybe no one bought the watermelons, maybe, right? It's just like, it just brings up a lot of questions. Now that we covered forces slightly, let's take a moment and talk about Newton's laws. And Newton's first law is often summarized as just inertia, which is not a bad way to think about it. Inertia as in things in motion stay in motion, things at rest stay at rest. And friction is the enemy here, at least the enemy of our intuition, of our understanding. Meaning, because we live on Earth and there's a lot of friction, we don't really see things kind of moving in a straight line forever. But what if you're in space? And here I have a picture of the Horsehead Nebula. This is like an actual part of space. It's freaking gorgeous. And let's just imagine here I am. All right, here's Mr. Ng. All right, just kind of thinking about life, thinking about watermelons. All right, just so confused. Right, and here I am just floating. So in space, I think you can imagine if something gives me a push, I'm just going to go in a straight line forever. Or if I'm still, I'm going to be still forever. That's inertia, right? And notice that the inertia could be at rest, right? And if it were on Earth and it was at rest, we would call this static equilibrium, right? Static means at rest. Or sometimes things are just traveling in uniform velocity. We call this dynamic equilibrium, because dynamic means moving, right? But long story short, if there are no net forces acting on you, then you're not going to have a change in velocity, right? So you're either going to stay still or keep on moving. That inertia was a huge part of Galileo's big experiments. I think you've heard about it. Galileo stands on top of a tower, drops things of different masses, right? So here we have 3 things of different masses, and they all have different mg's. Here's little mg, here's a bigger mg, and here's the biggest mg. So obviously they have different forces pushing them down, right? They have different forces. But even though C is being pushed down with a greater force, you need to remember inertia. At the same time, right, big masses have big inertias too. So this thing will have a big inertia, a moderate size inertia, a medium, or a small inertia, right? So here's our mg is being balanced out by inertia, which is why all things fall at the same acceleration if we ignore friction, right? But again, friction kind of sucks because usually, I mean, if we imagine a feather being thrown down versus a bowling ball, obviously the feather is going to be slow, but it's not slow because of its mass. It's slow because of air friction. So in a state without air friction, inertia will cancel out mg and all things fall at the same rate. Right? That's just inertia. Okay, so we already discussed Newton's first law. Things in motion want to stay in motion, things still want to stay still, unless acted on by a net force. And later on, we're really going to clarify what that net force means. Newton's first law, inertia. Newton's second law is often abbreviated as F is equal to m times a. Your force is equal to your mass times acceleration. And we already explained how this guy has a little force, this guy has a bigger force, and this guy has the biggest force, because their masses are different, right? Easy. I don't want to get too far into Newton's second, because we're going to have a whole couple of weeks about it. Let's talk about Newton's last law, Newton's third law. I think in the vernacular, most people would say that for every action, there's an equal and opposite reaction. And then Chuen-Wei was nice enough to quote what Newton said in his book Principia. Whenever an object exerts a force on a second object, the second object exerts an equal force in the opposite direction. So here's a crazy example from Chuen-Wei, really giving us winners in this chapter. A guy slams his hands at the corner of a table, like not any part of the table, but the corner of a table. Obviously, he's going to maybe move the table a little bit or exert a lot of force on that table, and it's going to freaking hurt because that table is going to exert that force right back. Good? That's the understanding that we need for now, but you are going to need to figure things out as you solve some questions tonight. So far in our lesson, we talked about what is a force, and we talked about some specific forces, tension, mg, friction, and then I gave you a very brief discussion of Newton's three laws, especially Newton's first about inertia and how inertia makes all things fall at the same rate if you ignore air friction. So here, the first time we saw this watermelon picture, we talked about the forces. Now, how does Newton's first, second, and third law apply to this picture? Please take a moment and use that as a way to write a summary for this set of notes, right? Like, where does the third law apply? I'll pause the video for a little bit so that you can think about it and put in your notes, right? Like she's just out there pushing those watermelon. I mean, I guess she's going to like a party where there's like everyone wants watermelon. She does seem pretty happy with herself. She seems really contented with all those watermelon. Okay, hey, let's talk about the various laws. Newton's first, if this thing was in space, if it was a space system with a woman in with the watermelon, then it would take a tiny step and she'll just zoom in one direction forever. Second law, because this thing is very heavy, this has a very large mass, right? And the acceleration might be pretty moderate. That means in order to move it, right, the applied force must be a pretty large applied force. Make sense? I think the most kind of crazy thing is Newton's third in this example. Because here's the thing. In order for her to move forward, right? In order for her to move forward, she needs to push back against the Earth. According to Newton's third law, the Earth is pushing her forward, yes, of course, but she's pushing the Earth back a little. The difference is she's tiny compared to the Earth. So every time you take a step, according to physics, I mean, you're applying a little bit of force on the Earth. And I mean, the Earth is moving you forward, propelling you forward. You move forward and you walk, but you're slightly, just a little bit, I mean, the Earth is huge, but just the tiniest bit, imperceptibly, you're also moving the Earth. Because for every action, there's an equal and opposite reaction. Weird to think about. Hey, thank you very much for taking down notes on this lesson. And you have some questions out of Chuen-Wei, and that should get us through this kind of very basic conceptual understanding of dynamics.